So, good morning, welcome back, and we'll see that this is the third lecture of module 5, where we are dealing with bridges, AC bridges in particular. So, we have already seen two types of Maxwell's bridges, where we have we have found a way to calculate the unknown inductance in terms of one bridge was in terms of calculated the inductance in terms of resistances, and the other, that is Maxwell's capacitance bridge, calculated the unknown inductance in terms of a standard variable capacitance. So these were the two bridges, and one thing I forgot to mention during that lecture was Maxwell's bridges are used to find unknown inductance having Q value, that is quality factor of the coil, less than 10. So for less than 10 quality factor values, coil having quality factor values less than 10, we usually prefer a Maxwell's bridge. There are other bridges which can measure coil Q values greater than 10. Example, Hayes bridge. Hayes bridge is one bridge which can measure in unknown inductance having Q values greater than 10. So that is not in the preview of our course. That is why I'm not taking that. And later we have seen one more bridge, that is shearing bridge, where we found the unknown capacitance in terms of some known quantities. And today we'll see the last AC bridge according to the KTU portion, that is Wien bridge. So Wien bridge we have often seen in the last semester. We have seen analog electronic circuits where we used Wien bridge in an oscillator. So Wien bridge has many applications. That is, it is mainly used in oscillators. That is, it mainly to generate audio as well as high frequency oscillations. And then it is also used as a notch filter. What is a notch filter? You may be learning that in S7 DSP course, where filter, as we know, it actually filters some frequency. That is the meaning of filter. So there can be low pass filters where it passes low frequencies only. There can be high pass filters where it passes high frequencies above a cutoff frequency, and there can be band pass filters where it passes the bit bands between two cutoff frequencies, and there can be stop band frequency also, where it actually passes low frequencies below a cutoff frequency and high frequencies above a cutoff frequency. And there is another type also that is called a null pass filter. It has some other uses. You learn that particularly in DSP course. And notch filter is one filter which allows only one particular frequency to pass. So Wien bridges are used to make the notch filters. These are the major applications of Wien bridge. So Wien bridge is actually a Wheaton's bridge. It also has its 4 arms, but only thing is that we have a supply with an unknown frequency. So the other 2 arms are having combinations of resistance and capacitances, just like you are seeing here. One arm is having series combination of resistance and capacitance, and another is having a parallel combination of resistance and capacitance. So unlike the previous bridges, so in the previous bridges we have learned that you simply keep this as a constant at some magnitude and some frequency, and you adjust the variable element so that at some particular value this detector will show null deflection, so that we say that bridge is balanced. But here the case is reverse. We keep the parameters constant. We keep this R1 and R2 constant at some value, and then we have a supply with some magnitude and with some frequency. So we are actually varying the frequency of the supply, which has to be known, so that at some frequency the bridge will get balanced. So that is the unknown frequency. So we have to know under what frequency this bridge is getting balanced. So we keep on changing the frequency of the supply so that this at one frequency the bridge gets balanced. So we here also use the same balance principle, that is Z1 Z4 is equal to Z2 Z3. We apply everything here. We segregate the real parts and imaginary parts on both sides, and you can see that this ratio will be equal to this ratio only at one particular frequency. So keeping that in mind, equating the real and imaginary parts, you will get this one, and from that omega is an angular frequency, So omega, if omega is angular frequency, you can find the frequency value also. So that is f is equal to, that is omega is equal to, you know what is omega. So substitute that is omega is 2 pi f. So this 2 pi will be coming here. You will be getting this equation. So if you keep R1 equal to R2 equal to R and C1 is equal to C2 is equal to C, then you'll get that this is equal to 1 by C, simply 1 by 2 pi RC. This equation is we have seen in the Wien bridge oscillator, that is this one. So if we keep, that means if you make R1 equal to R2 and C1 is equal to C2, we have a case here, that is equating, when you equate the real parts, we have this case, that is R2 is equal to R1, that means this will get cancelled, that is equal to 1, and C1 is equal to C2, this gets cancelled, this will be also be equal to 1. So 1 plus 1 is equal to 2, so that we can get that R4 by R3 is equal to 2. That means R4 is nothing but 2 times the value for R3. So these are the things, so we have to remember, in under these conditions the bridge will get balanced. So you have to select the values of R1 and R2 in such a way that they are equal, C1 and C2 such a way that they are equal, and the R4 is equal to 2 times R3. Under this condition, you can get one frequency. You can select a frequency. So you can determine frequency using a Wien bridge. So this is all about Wien bridge, a very simple bridge. It can detect frequencies from 100 hertz to 100 hertz to 100 kilohertz by varying the quantity of this R1 and R2. That is why we have a common variable quantity, common variable, because we have to make these two R1 and R2 equal. Now we are moving to another section, that is potentiometers. In particular, we'll see DC potentiometers and AC potentiometer. At the onset, we'll see what is DC potentiometer. Potentiometer generally we know, that is, it is used to find the unknown EMF. That is what we know from the basic +2 classes. And one more application is there. You can compare two EMFs also. And we all know the principle of operation of a potentiometer, that is the potential gradient, that is V by L is a constant, that is V directionally proportional to L. Whatever is the voltage drop is directly proportional to the length, the length for null deflection, for obtaining the null deflection. So now one more application is there. Potentiometer is actually the absolute standard for measurement of voltage. So why it's called an absolute standard? See, voltmeters can be compared with, or they can be calibrated with a potentiometer. Why? Because potentiometer will follow a null deflection technique. That is, it will not draw any current from the source. But if we take the case of voltmeter, even though we have very high impedance for a voltmeter, still a few microamps or milliamps of current will flow through the voltmeter, so that it will deflect. So that small current drawn from the supply will actually load the source, however, to some extent, and then the reading of the voltmeter will always be less than the actual voltage. That is, it has some drop inside the voltmeter. That is why after that drop only the voltmeter will show some deflection. So the reading or the indication of the voltmeter will be actually less than the actual voltage. So that is why we always prefer potentiometer as an absolute method. That is, it follows null deflection. It will not draw any current from the source. Now this is the basic diagram of a potentiometer. That is, we have a slide where which is of uniform cross section. Uniform cross section in the sense it's a uniform area, cross section area. And one more thing is that we ensure that at per 1 centimeter we have 1 ohms. That is 1 ohms per 1 centimeter. So if we have a 200 centimeter slide wire, then this total resistance of the slide wire will be 200 ohms. That means per centimeter we have 1 ohms. Now this is my slide jockey, and where I have my galvanometer. So suppose if I close this switch and put the switch in the operate position where the circuit is connected to the unknown EMF. So this unknown EMF will send some working current through the supply. So the working current can be controlled by this rheostat. So if you scroll this, or if you slide this jockey over the slide wire at some particular length, say E1, we see a null deflection in the galvanometer. So this E1 is directly proportional to the length here. So knowing the length here, you can easily calculate the value of E1, which is equal to E, which is nothing but the unknown EMF. So this is how the basic potentiometer works. Now before doing that, I talked about working current. So what is working current? So working current is a current which we have to maintain in the circuit. So that working current we have to set initially by a procedure called standardization. That is, initially we have to place this switch instead of operate position to a calibrate position. Initially the switch should be in calibrate position, and that is where we start the procedure for standardization. That is, while we keep this switch to calibrate position, instead of the unknown EMF, we have the standard cell connected to the bridge, the DC potentiometer circuit, and we know that the standard cell is having a voltage of 1.0186 volt. It was there. So 1.0186 volt, and the procedure for standardization is that you keep, I told that per centimeter there is 1 ohm drop. First you keep this jockey at 101.86 centimeter. I repeat, after closing the switch to calibrate position, you keep the jockey at a length of 101.86 centimeter, and then you adjust this rheostat so that we'll get a null deflection in the galvanometer. So after positioning your jockey at 101.86 centimeter, you adjust this rheostat so that we obtain a null deflection in this galvanometer. So what is the meaning? The meaning is that is you have meaning is that you have the standard cell voltage of 1.0186 volt, and you have the resistance. I have kept the length at 101.86, so my resistance also will be 101.86. So voltage divided by current, voltage divided by ohms, we'll get the current, which is nothing but 10 milliamps. So by standardization, we mean that we are setting a current, working current of 10 milliamps. So what is so advantageous of setting this 10 milliamps here? So if we set 10 milliamps here, suppose, so for 1.0186 volt, we have a length of 101.86. So, or a resistance of this one. Suppose if we have a voltage, if we have a null deflection at 1.5 volt, let us suppose that we have a null deflection at 1.5 volt for some unknown voltages. So if we have the drop at 1.5 voltage, then this 1.5 volt divided by 1.5, okay, so that means that the 1.5 volt will correspond to 150 centimeters. That is how it is 150 centimeters. 150 centimeters means 150 resistance, ohms resistance. So that 150 ohm resistance multiplied by 10 milliamps current will correspond to 1.5 volt. That is a meaning. So simply knowing the length, we can simply get the value for voltage. That is, if the length, if the length is 150 centimeters, where we get the null deflection, easily we can tell that it is 1.5 volt. Whereas if the sliding length is 160 centimeters, where we get the null deflection in the galvanometer, we can easily tell that it is 1.6 volt. From that, from the length, we can easily get the value for the voltage. That is the meaning, that is the advantage of having a working current of 10 milliamps. I hope you get the point. So after setting this 10 milliamps working current, you can actually keep the switch from calibrate position to operate position, so that for some unknown EMF, if the unknown EMF is, suppose if it is 1.5 volt, then surely the sliding contact will come at this point, that is 150 centimeters, so that we'll get a null deflection of galvanometer. In the galvanometer, we can tell in the other way also, that is, if you suppose if we have a null deflection at 180 centimeters, then you can easily tell that the unknown EMF is 1.